All right, let's work some problems. Let's look at number 24, chapter 10. Okay. We have a hollow spherical shell with mass 2 kilograms, rolls without slipping down a 38-degree slope. Find the acceleration, the friction force, and the minimum coefficient of static friction needed to prevent slipping. That's part A. So let's do A. So let's draw. I'm going to do my axis here. And I'm going to assume that's about 38 degrees. So theta is going to be equal to 38 degrees. Here's our ball. There's no slipping. So static friction only. Let's finish our diagram. And if you remember when we were looking at frictional forces and forces on an incline, you have to draw all your vectors for all your forces involved. And we know this is the force normal right there. And we know on a on a flat surface, we know that what? The force normal is equal to mg, right? But it's not on a flat surface. Where is mg? Well, we know that the gravity always pulls straight down towards the center of the earth. So there's gravity, or weight, the weight's going straight towards the center of the earth. So let's finish our triangle here. Now, since it's on an incline, we know that the weight is not going to be distributed this way because it's a rigid surface. It's going to be distributed this way. So what vector coincides with the direction of the distribution of the weight? Okay, the force of weight is causing it to roll. Its own weight is causing it to roll due to gravity. So this vector coincides with the direction it's going to move, right? And since we know mg and opposite over hypotenuse, then this is mg sine theta. And then we also know, since this is adjacent over a hypotenuse, this is mg cosine theta. That right there is. Okay, that is mg cosine theta. All right. Now, something else we need to label. We need to label our frictional force, which is that way. That's frictional and it's static. Okay. It's always in the opposite direction. Frictional force is. All right. So what then else do we know? What else do we know? Well, we know that the moment of inertia, this is a hollow spherical shell. We know that the moment of inertia is equal to what? 2/3, because it's a hollow spherical shell, mr squared, and that's center of mass, and that's a 2. Okay. What else do we know? Well, is it accelerating? Well, the gravity's pulling on it, and so yes, it is. It has to be accelerating because of gravity. So then the sum of all forces is equal to what? ma, because it is accelerating down the ramp. So actually, we're going to be looking at acceleration center of mass. So it is accelerating. Now, all right, what else do we know? All right, well, we know that there's also going to be torque. And how do we find torque? Well, one way we can find it, and the most useful way we can find it, since it's rotating, is taking the moment of inertia times the angular acceleration. All right. Now, we also know that torque is what? Torque is also found this way, force cross product R, right? Okay? Force times R, the radius. But since it is a cylindrical object, a hollow spherical shell, we need to use the moment of inertia. It's real important, okay? And how do we find angular acceleration from acceleration center of mass? Well, angular acceleration is equal to the acceleration center of mass divided by the r, is it not? Yes, it is. Okay, so let's see what we can do now. Let's go from there. All right. Now, how do we, remember we started with the sum of all forces, right? So let's sum up all the forces at work. The sum of all forces is equal to what? Well, we have the weight being distributed at an angle. So we have that is the actual applied force, okay? Mg sine theta. Then we have the frictional force, which is in the opposite direction. We've already drawn that. And it's all equal to what? MA. Okay? So we have, it's accelerating down the ramp due to what? Due to the weight at an angle, and then it's also being affected by the static frictional force, which will be subtracted out. Well, that's great, isn't it? So we know that, but now how do we find the static frictional force? Well, let's go back and look at torque. And you say, one of the three things we had to do is find the frictional force. We also had to find the coefficient of static friction. Well, y'all, we don't have the coefficient of static friction. It didn't give us that. Okay, so what do? Well, we just have to think a little bit. So now let's go back and look at torque. Let's go back and look at torque. All right, remember torque by definition is what? Well, torque, and since what is affecting the object's torque? Well, friction is. So the frictional force times R, which is torque right here. We're looking at this equation right here. And we're substituting. And you say, well, why didn't you use a capital F? Because the force affecting the rolling is the frictional force. So the frictional force times R is equal to, well, what's the moment of inertia? Well, it's 2/3 mr squared. And then we have our alpha over here, alpha. Okay. Now you say, where are you going with this? Y'all, I'm trying to isolate or solve for the static frictional force. Well, how are we going to do that? Well, we've got to do a little more substitution. All right, we also know the angular acceleration, so substitute right here, okay? So everybody sees what I'm doing here. I substituted this for torque, okay, except we're using frictional force. So now let's substitute right here. So we got the static frictional force times R is equal to 2/3. Boy, I wish this pen would quit doing that. 2/3 mr squared, and then substitute for angular acceleration center of mass over R. Now watch what happens. Now let's do some simplifying. Okay, this R cancels out the square. Divide both sides by R. Right here. This cancels out. That cancels out. And we're left with the frictional static force is equal to 2/3 m times acceleration center of mass. So now we can find the frictional force. Okay, and that's very, very important. Now we can go back to this equation. So we're going to take this equation and we're going to take this equation and we're going to combine them. Or we're going to do some substitution basically. Okay, so let's do that. Let's go to the next slide. All right, so we substitute the frictional force, and what do we get? Well, we get mg sine of theta minus 2/3 ma center of mass, which is equal to ma center of mass. Okay. All right. Now let's do some more simplifying. Okay. Let's divide both sides by m. Capital M, and cancel. And now we're left with g sine theta minus, now I could have actually waited and done that, but either way, okay, either way. Because there's your common denominator, so each one, all right now. So g sine theta minus 2/3 a center of mass, which is equal to a center of mass. Now let's get our like terms on the same side. So what are we going to have to do? We're going to have to add a 2/3 ma center of mass plus 2/3 ma center of mass. Well, what does that do? That cancels it out here and leaves us with what? G sine of theta is equal to a center of mass plus 2/3 a center of mass, okay? All right, now, let's get, notice we got an a and a 2/3 a, okay? Well, A is the same as saying what? 3 over 3, isn't it? A, which is 1, is the same as saying 3 over 3A or 1A. Okay? You say, well, why are you doing that? Because you got a fraction. And so we got to add both those terms together. And the only way we can do it is with fractions. Now, here's our common denominator. Notice you say, well, why did you pick 3? Well, look, over here the common denominator is 1, and here it is 3, so we pick 3. Okay, so add them together, and what do we wind up with? We wind up with g sine theta is equal to, well, 3 plus 2 is 5/3 a center of mass. Now we can solve for a center of mass. So let's do that. So a center of mass then is equal to what? 3g sine theta divided by 5. Now, y'all, the physics is over with. So now all we got to do is start substituting our values. So we get 3 times 9.8 meters per second squared times what? Sine of 38 degrees divided by 5. And we get an acceleration center of mass of 3.62 meters per second squared. So there's your acceleration center of mass. Okay. Now, how do we find the frictional force? Well, if you remember, we've already said that the static frictional force is 2/3 ma center of mass. So we got 2/3 times 2 kilograms times acceleration center of mass, 3.62 meters per second squared, and we get 4.83 newtons. Newtons, that's an N. Boy, this thing's really starting to irritate me. It don't, you've got to be kidding me. All right. Okay, there we go. Newtons, all right. There's your frictional force. All right, now we've got to do one more thing. We've got to find the coefficient. Well, if it will advance a slide, we've got to find the coefficient of static friction. Well, how do we do that? Well, you remember static friction is equal to mu of s mg. But now it's not on a flat surface, it's on an angle, so it has to be, oh boy, cosine theta. Okay, so mu of s mg cosine theta. So solve for mu of s. So mu of s is equal to the static frictional force divided by mg cosine theta. And so our frictional force was 4.83 newtons divided by, we got 2 kilograms times 9.8 meters per second squared times cosine 38 degrees. And so the mu of s is equal to 0.313. There's your coefficient of static friction. All right, now let's look at 24b. 24b says what? What would happen if the mass doubled? Okay, well, if you go back and look at your equations, well, anyway, we see that the acceleration is independent of the mass. Okay, so the acceleration is not going to change. And when you look at your frictional equation, if you double the mass, you double the friction. So the friction, you double friction. And then if you look at your equation, you see that when you solve for coefficient of static friction, you've got mass here, you've got mass there, they cancel each other out. So the friction is not affected. Friction is not affected. Okay? All right, now let's go ahead and look at number 25. 25 is a little bit involved too. All right, see if I can advance slides here. All right. 25 says we have a 392 Newton wheel comes off a moving truck and rolls without slipping along a highway. At the bottom of the hill, it is rotating at 25 radians per second. Okay. So we've got, this is 20, I'm about to get really aggravated. 25. Okay. All right, so doing something like that, comes off, goes down the hill, going to wind up right back up here. Okay. All right, so the weight of the wheel is 392 newtons. Okay. So let's go ahead and find the mass. We know that weight is equal to mg, and therefore m is equal to the weight divided by g. So the mass of the wheel is going to be what? 392 newtons divided by 9.8 meters per second squared. And we get a mass of the wheel is going to be, oh, I've got it written down somewhere. I thought I did. 40 kilograms. Okay, 40 kilograms. All right. Okay, so we've got that out of the way. And it says at the bottom of the hill, the angular speed is 25 radians per second. I see why it's not writing now. All right, it's 25 radians per second. Y'all, I apologize. 25 radians per second. My pen's trying to come apart on me. Okay. And then it says the radius of the wheel, and you can use big R, little r, doesn't matter, is 0.6 meters. Okay. And the moment of inertia is 0.8 mr squared. Okay. Moment of inertia is 0.8 mr squared. Friction does work on the wheel as it rolls up the hill to a stop. So we know that friction is in the opposite direction, static friction. And by the way, there's no slipping. Okay, so it's just static friction. Yes, okay. All right, now, and it has an absolute value of work. The work value is 2,600 joules. Okay. So from start to finish, it's 2,600 joules. So this is going to become a work kinetic energy theorem. Okay. All right, well, first of all, let's look at the rotational kinetic energy. We know that rotational kinetic energy is two equations. It's 1/2 I omega squared plus 1/2 mvr, and that's center of mass squared. MV, center of mass squared. So since this wheel is rotating, there's two things going on. You've got the moment of inertia of the wheel, and you've got the translational, or the center velocity, center of mass, translational velocity of the wheel. You've got those two components, or those two quantities at work on the wheel. So as I said a minute ago, this is going to become a work kinetic energy theorem. Okay, I believe that's. Am I saying that right, or am I saying it wrong? Okay. Total mechanical energy. Okay, total mechanical energy. All right, so we have initial, potential, and kinetic plus work other is equal to the kinetic final plus the U final. All right, now let's do some more defining of our terms here. Well, what is the final kinetic energy when it stops? Well, final kinetic energy is 0 joules. All right. Yeah, sure, think about it. And what is the initial potential energy? Well, the initial potential energy is 0 joules. Okay. All right, so this term is gone, and that term is gone. All right, so now let's do some substituting, and let's look at our initial kinetic energy. So how do we determine the initial kinetic energy? All right, while it's rolling. Well, the initial kinetic energy, all right, well, look right here. You see this equation right here? You see that right there? We'll substitute for the moment of inertia. So we have 1/2, and when we substitute for the moment of inertia, which is right there, what do we get? We get 0.8 mr squared omega squared, see right here, plus 1/2 mv center mass squared. Okay. All right. I've left something off. What have I left off? What have I left off? Hang on a minute. Okay. I also forgot one other thing. I had to look at my notes. The velocity center of mass is equal to what? R times what? R times omega. Okay. So, well, let's substitute that right here. That's what I was forgetting. So let's substitute this right here. We're going to substitute that right there, and it becomes what? It becomes R squared omega squared. Okay. Now we have like terms. Well, you have a half here and a half there, and a half plus a half is 1. And so what is this? It's 0.8 mr squared. So if you add 1 more tenth to it, the kinetic initial energy becomes 0.9 mr squared omega squared. Okay. So now we can start chugging, and now we can start plugging in. So we know our kinetic energy is 0.9, the initial is mr squared omega squared, plus work other, and work other is going to be the work done by friction, which is equal to, well, how do we find the potential energy? Well, it's mgh. Now, what are we looking for here? We're looking for the height, aren't we? Calculate h, okay? So we get mg GH, right there. So let's calculate now for height. So height becomes what? Well, we've got 0.9 mr squared omega squared, all right, minus, plus work done by friction, because work other is friction, and of course it's going to be negative, so the work done by friction has to be, I thought I'd already written this down, I haven't, negative 2600 joules, all right, divided by mg, okay? So now let's plug everything in. So we get, let me go to the next slide. I'm running out of room. So height is equal to 0.9, and what was the mass? The mass was 40 kilograms, times the radius, which we said was 0.6 meters, squared, times the angular velocity, squared, minus 2600 joules, that was the work done by friction, divided by 40 kilograms, times, 40 kilograms times 9.8, and the height is 14.0 meters. Now I know you get an answer like 14.03, so that just rounds down, okay? 14.0 meters. All right, I want to pause for